In one of the previous videos, we learned about the law of sines, and today we're going to learn about the law of cosines. So let's jump in by taking a look at a problem where the law of sines would not be helpful to us. So here we have it. Here's a problem where we have to find the length of segment BC, and it says the law of sines cannot be used on this problem. Why not? Well, let's take a look at what would happen if we tried to use the law of sines. Remember, the law of sines says that if I take the sine of angle A over side length A, which is of course the side that would be across from that angle, that ratio would equal sine B over side length B and would be equal to sine C over side length C. So you can see we have triangle ABC over here. Let's go ahead and label the sides as which one would be side A, side B, and side C. So across from side A, we would have, across from angle A, we'd have side A, and then we'd have side B across from angle B, and then side C across from angle C. Now, if we filled in these three amounts into our relationship that the law of sines tells us will be true, we'll see what we have. So I'm going to put sine 57 over A equals sine of B, since I don't know the measure of angle B, over 10, and that's going to equal the sine of angle C, since I don't know the measure of angle C, over 8. Now, the reason why the law of sines doesn't help us here is because what we would typically do is we would then typically pick two of these three fractions, set them equal, and cross multiply to solve for one of the unknowns. But the only way that works is if you think about each set of two, there'd be four spots: a numerator, denominator, numerator, denominator. We need to have numbers. We need to have known values in three of those four spots in order for us to solve for the one that would be missing. But if you look here, if I pick these two, I have an unknown here and an unknown here. If I pick these two, I have an unknown here and an unknown here. And if I pick the first and third one, I have an unknown amount here and an unknown amount here. So no matter what combination of fractions or ratios I'm picking here, I'm not going to be able to pick a combination where I know three of the four things and I'm able to solve for the one thing that's missing. No matter which two I pick, I'm going to have two unknowns. So the law of sines would not help us here. However, if we think about what this triangle looks like, this is kind of like I described in the last video, this is a unique triangle. If I have a 57-degree angle here, I've established the angle that these are going to be sitting at, and I've established how long this side is, 10 units, and how long this side is, 8 units. There's only one option for where segment BC would be. It would have to start here and end here. So the length of this is kind of predetermined. It's predetermined by the angle that these two sides are sitting at and how long they are. And if that angle is if that length is predetermined, then that means also that these angles have kind of been predetermined, if you will, by the fact that this side, and this angle are all specified as to what their measures should be. So what I'm trying to say is this triangle would be unique. If I have a 57-degree angle here, a side that's 8 here, and a side that's 10 here, there's only one triangle that could be created with those measurements. And what that means is we should be able to figure out, logic would tell us we would be able to figure out how long this side is, what that angle would have to be, and what that angle would have to be. But the law of sines is not going to be what helps us do it. It's going to be something called the law of cosines. So the law of cosines is similar to the law of sines in that it works for any triangle. If we call a triangle ABC that has side length A across from angle A, side length B across from angle B, and side length C across from angle C, if we look at that triangle, there's a relationship between the cosine of any angle in that picture, in that triangle, and the side lengths that make that triangle. And that relationship looks like this. Okay, this is three different versions of basically the same thing. It's just, if we look at the first one, we have A squared equals B squared plus C squared minus 2 times B times C times the cosine of A. Okay, now that's a mouthful. That's a lot going on there, right? But you can see that it's using the side lengths of the triangle, A, B, and C. It uses B and C actually twice, and the cosine of one of the angles. And it's showing this relationship that exists. Now if I change the angle that I'm taking the cosine of, then I essentially change where the a's, b's, and c's go in the rest of the equation. And if I change it to angle C, then it changes again. So these three things are really just reorganized versions of the same rule for a triangle like ABC. The way I think of it is if I have side A all by itself over here where it says A squared, then these two spots will be for B and C, side length B and side length C. We'll have B squared and C squared added together, and then out here in front of the cosine, I'll have 2 times B times C. So when A is out here, BC, BC, right here, and then the angle matches the A that's out here. So side length A out here means I'm going to have cosine of angle A here. When I switch it to side length B out here, then I have A, C, A, and C, and then the angle that the cosine is going to matches the angle that would go across from the side that's over here, B. So B squared is A squared plus C squared minus 2AC cosine B. And then finally, if I change it to side C, then the other two, A and B, they get used A, B, in these 4 spots here, and then the cosine goes for angle C, just like it is here. Now this looks intimidating when you first glance at it. It looks like it's going to be a lot to memorize, and it kind of is in a way, but I'll tell you, you don't actually need to memorize all 3 of these things. You can memorize just one of them, and you can use that in any situation, and we'll learn as we do some of the example problems for this stuff. We'll see how we really only need to know this top one, and we can use it, make it work in any situation where we want to use the law of cosines. And the other thing is, as you're doing practice problems using the law of cosines, my best advice is to write out this law of cosines every time you use it, because if you write it out every time you use it, you're probably going to have to look it up the first few times you write it out. You'll have to have like your notes next to you and kind of peek over at your notes to make sure you write it correctly. But then as you keep doing that, eventually you're going to have it committed to memory, and you're going to be able to write it without peeking at your notes and without having to look and see if you're doing it correctly. It'll kind of roll off the tongue, just like A squared plus B squared equals C squared does, or just like any of the other kind of relationships in math that we can think about without even really trying. So that's called the law of cosines. There's a proof for why it works. I'm going to make this video a little bit shorter. I'm not going to do the proof in this video. I'll probably put a link up that has a proof of why the law of cosines works. But there is a proof that it always would work. But the question we want to ask is, what can we use this for? What can we use this law of cosines for? Why do we want to know it? If you think back to the law of sines video, we talked about how we can use the law of sines to find missing angles or missing side lengths on triangles that are not right triangles. I mean, technically it works on right triangles as well, but we don't have to have a right triangle if we want to use the law of sines to find an angle measure that's missing in a triangle or a side length that's missing in a triangle. But like we demonstrated at the beginning of the video, the law of sines won't always work. So what we use the law of cosines for is we use it to find missing angle measures or side lengths in a triangle, in any triangle really, when the law of sines won't work. And I say it that way because the law of sines is a lot easier to use. It's easier to remember than what this is, and it's just generally going to be easier to kind of work out and solve an equation that uses the law of sines. But if the law of sines doesn't work, like we saw in that example a few minutes ago, then what we can do is we can use the law of cosines for that example, perhaps, to find whatever angle measures or side lengths might be missing. So that's what we're going to use the law of cosines for. It's like our backup tool when the law of sines won't work. So why don't we go ahead and try and figure out under what circumstances we would be able to use the law of sines, and under what circumstances would we have to use the law of cosines instead. And so what I typically think of is I can use the law of sines. You know, if you remember what we talked about a minute ago, with the law of sines saying sine A over A equals sine B over B equals sine C over C, We can use this as long as we can pick out two of these ratios, maybe the first and second, maybe the second and third, maybe the first and third, and three of the four parts in the ratio actually have measurements. So for instance, we would have a measurement here, and maybe one there, and then we'd be able to find B. Or maybe we would have we'd have an angle measure there, we'd have a side length there, we'd have a side length there, and we would be able to find the measure of angle A there. As long as we have two ratios that we can pick where three of the four measurements are known, that's when we can use the law of sines. Well, we can boil that down further. In order for three of the four measurements to be able to be known in any pair of ratios here, really what it means is we have to have one angle and its opposite side and some other piece of information. So these two pieces of information and this one, these two pieces and this one, these two pieces and this one, these two pieces and that one, and just some combination where we have both the angle measure and the opposite side length plus one other piece of information. That would be enough to use the law of sines. So let me write that down. We can use the law of sines when we know one angle and its opposite side plus one other measurement, meaning one other angle measure or one other side length. If we have that information, then we're going to be able to use the law of sines. So let's think about what would a picture have to look like so we would know this. Well, what if I had a triangle? Okay, let me sketch out a triangle. And what if I knew this angle, and this side? So I'm just going to use these markings to show. Maybe I'll use a different marking on the two angles so it doesn't look like they're congruent. I know these pieces of information, whatever the number of degrees is here, whatever the degrees is here, and whatever that side length is there. If I know that, then I can figure out this side, right, using the law of sines. I could technically even figure out this side. I would have to first maybe subtract these angles from 180 to get this one, and then I would have this angle and its opposite side plus this angle would let me find this side. The way it sits now, knowing this angle, this opposite side plus this angle, I can find this side. So what we call this the angle side case. Right? So we can use the law of sines in the angle side case, which means that we have two angles and a side that's not included between them. Right? We talked about angle side back when we were dealing with proving triangles congruent. It's the same idea. So as long as we know two angles and then a side that's not between them, we can use law of sines technically to find any other piece of information about that triangle. And then there's one other situation where we're going to have what I've written in purple there. So let's say I have another triangle here. Let's say I have this side, this angle. So I have, again, one angle and its opposite side. And then let's say I also have this side length right here. All right, so I have my angle and its opposite side plus my one other piece of information. This is what we call the side-side angle. I have two sides and then the angle that's not in between them. In the side-side angle case, that sometimes in that case sometimes we're able to use the law of sines, right? This is only sometimes. And the reason that it's only sometimes is if I have this information, sometimes there won't actually be a triangle that can be made using certain measurements for this angle, this side, and that side. Sometimes there's actually going to be two triangles that could be made using a certain combination of angle measure, side length here. So as you get into higher level classes, Algebra 2 and Pre-Calculus, you'll learn under what situations the side-side angle case works and under what situations it doesn't really work. But for our point right now, the law of sines would be our option if we're presented with a side-side angle case, meaning that we have maybe this angle measure, this side length, and then this other side length here. We could maybe use side-side angle, or maybe use the law of sines to find out a missing measurement of either an angle or the other side there. So those are the two situations where we can use the law of sines. There's two other situations where we can use the law of cosines to find out missing parts in a triangle. So let me sketch out one of them here. Actually, one of them is what we just saw at the beginning of this video, which is where we know this angle, we know this side, and we know this side. And we call that the side angle side case. In the side angle side case, we know two side lengths, and we know the angle that's formed by those two sides. So again, I'm putting markings here, but really in the problems that we'd be working with, we'd have actual measurements here, like maybe that say like 9, 12, and 42 degrees. All right? We'd have actual measurements for all of these markings that I'm putting on these triangles. In this case, the side angle side, we should be able to use law of cosines to find missing, specifically what we'd be able to find is this side over here. We'd be able to find this third side here using the law of cosines in this problem here. The other situation where we're going to use the law of cosines, and this one's a little bit trickier, is if we have all three sides. So we call this the side, side, side case. In the side, side, side case, we can use the law of cosines to find one of the angles that we might be missing. Okay? We might be able to find this one, or we could find that one, or we could find that one, just depending on how we kind of arrange the law of cosines. And then we'd be able to find an angle. Now, in that case, if we wanted to find some other information, like so for instance over here, if I use the side angle side, or if I use the law of cosines in the side angle side case, and I found this side, well now I could go and use the law of sines to find some other piece of information. I could find one of these other angles using the law of sines, because then once I know this side, I've fulfilled like this requirement. I know an angle and then its opposite side, plus I could use one of these other pieces of information, and I could use the law of sines to find one of the other angles. And then the same thing could happen here. If I use the law of cosines to find this angle, then I could go on and use law of sines to find one of the other angles if I wanted to. But in general, when you see a problem where angle, angle, side is given, so these two measurements and then maybe this side is given, or if it's side, side, angle, then you want to use law of sines. If it's side, angle, side, where I know two side lengths and then the angle between them, or it's side, 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 meaning I gave you all three side lengths, that's when you're going to want to start by using the law of cosines to find a piece of missing information.